right, so today we are going to discuss the ascent and descent of Cohen-Macaulay and Gorenstein property under flat local homomorphisms. We have proved preservation of Gorenstein property under many operations. Suppose Rm is Gorenstein, then this implies that R localized at P is Gorenstein for all primes P. It also implies R mod XR is Gorenstein if X is a non-zero divisor. Okay, and converse also holds. What we have not yet proved is, suppose, so what about Rx or power series, yeah, or the MAD completion. So we will show that all these rings are also Gorenstein. These are also Gorenstein. So Gorenstein property is preserved under all these operations: localization, going mod a non-zero divisor, formation of polynomial ring or power series ring, or passing to completion. So it's a very stable property in that sense. We are going to prove the preservation for Rx and power series and R completion as a consequence of study of this property under flat local homomorphisms. Okay. Rx over R is a free module. R to Rx. This is free. Rx is free, so this is flat. This is a flat map. Yeah, and maximal ideals don't blow up to the whole ring. So this is also faithfully flat. Okay, this is also faithfully flat. Similarly, the power series ring in one variable over R, that is a flat map, and maximal ideal goes into maximal ideal. And R to R completion, MAD completion, this is also a flat map. That is, R completion is a flat R module, Rx is a flat R module, R power series ring in X is also a flat R module. So these three, and RP is a flat R module. Yeah, localization is a flat R module. So it becomes important to study the behavior of Gorenstein property and Cohen-Macaulay property, or take any other singularity. How does it pass through a flat local homomorphism? Yeah, so let me recall what is flat local homomorphism. So suppose Rm, this is local ring, and these are local Noetherian rings. And F is a homomorphism, ring homomorphism from R to S. Okay, this is called flat local homomorphism if S is flat R module via this map, and maximal ideal of R is mapped into the maximal ideal of S. Okay, this I'm denoting by N, and this I'm denoting by M. Okay, we will also need the residue fields. So I will denote residue field of R by K and residue field of S by L. Okay. So all these three homomorphisms from R to Rx localization at a prime ideal. Then if R is local, our power series ring in X is also local. And R completion of a local Noetherian ring is also local. Okay. So these maps from R to these three rings, they are flat local homomorphisms. Okay. So we want to just a minute. Some problem. My screen seems to have disappeared. Just a minute. Maybe I need to share it again. Okay, are you able to see the screen now?
Yes, sir.
Yes.
Okay. All right. So we have this flat local homomorphisms, and we want to understand what is the relation between Cohen-Macaulay property and Gorenstein property of R versus the same properties for S. Okay, right? So this requires certain formulas about dimension and depth and preservation of flat local homomorphism under certain maps. So finally, at the end, we will prove that S is Gorenstein if and only if R is Gorenstein and the closed fiber is Gorenstein. That's what we want to show. This will be the end theorem that R is Gorenstein respectively Cohen-Macaulay, if and only if S, okay, S is Gorenstein, if and only if the base is Gorenstein and the closed fiber, okay, R mod M tensor S, okay, this is Gorenstein or Cohen-Macaulay. This is the final result I want to show. And this result will imply that if R is Gorenstein, Rx is Gorenstein, R power series ring is Gorenstein, R completion is Gorenstein. Let me derive this consequence first before we embark on the proof of this result. Okay. So corollary. If R is Gorenstein, then the M-adic completion is also Gorenstein. Okay. So to prove this R relation between R and R completion, you just observe that this map, which is really inclusion map from R to R completion because of Krull intersection theorem, this is inclusion map. And this is flat local homomorphism. In fact, more happens here because the maximal ideal of the completion is really the extension of maximal ideal of R. Okay. So what is the fiber? Fiber is R completion, MR completion. And this is also isomorphic to R mod M. These are basic facts proved in Atia McDonald. You can check that R completion over MR completion is isomorphic to R mod M. Okay, this is a field, and certainly it is Gorenstein ring, yeah, Cohen-Macaulay ring, and so therefore R completion is Gorenstein or respectively Cohen-Macaulay if and only if R is Gorenstein, Spittle Cohen-Macaulay, and the fiber is a field. Okay, so that is clearly Cohen-Macaulay and Gorenstein. So this implies this passage of Gorenstein and Cohen-Macaulay property from R to R completion and vice versa. So in many situations, you want to prove that certain local ring is Gorenstein, we can pass to the completion and use Cohen structure theorems. We say that complete local ring is a homomorphic image of a regular local ring. Regular local rings are very well behaved. And and Gorenstein property will descend to R. So this is a usual trick employed to test Gorenstein property of local rings, that you can pass to completion and realize the completion as a homomorphic image of a regular local ring. Yeah. Let's look at the second corollary. R is Gorenstein. Same property with Cohen-Macaulay. If and only if Rx is Gorenstein. X is indeterminate. Okay, so proof. Gorenstein property is a local property. Rx is not a local ring, although R to Rx is a flat map. So we need to, this is a flat map because it is a free module. I need to prove that Rx localized at any prime ideal is Gorenstein. So localize at a prime ideal or maximal ideal. Yeah. Suppose Q is a maximal ideal. Of Rx. And this is flat. And this is also flat. Yeah. So and composition of flat maps is a flat map. What I do is I take the intersection of capital Q with R. Okay, this is intersection, right? And so the localization of Rx at Q is same as I can first localize at the contraction and then localize at the extension of Q to RQX. Okay. RQ is Gorenstein. If R is Gorenstein, then RQ is Gorenstein. This is a Gorenstein local ring. So we are taking polynomial ring over a Gorenstein local ring and then localizing at any maximal ideal. So we may, without loss of generality, we may assume R is local. R is local. Okay, and Q is maximal ideal. Q is a maximal ideal. Is the maximal ideal. Okay. And then I need to check that whether Rx is localized at Q, whether this is Gorenstein. Okay. Now this is flat local map because now R has become a local ring. Okay. R has become a local ring. So maximal ideal of R will go into, because maximal ideal of R is contraction of Q, maximal ideal of R is mapped into the maximal ideal of Rx Q. So this is a flat local homomorphism. So I have preserved the assumption. Okay. So this is a flat local homomorphism. And under flat local homomorphism, the base is this ring is Gorenstein if and only if base is Gorenstein and the fibers are Gorenstein. Okay. So RxQ is Gorenstein if and only if R and the fiber over the maximal ideal. Yeah. So RxQ MXQ is Gorenstein. I'm assuming R is Gorenstein, so I need to just look at this fiber. But this is isomorphic to R mod M X localization at Q. This is a principal ideal domain. Okay. And in principal ideal domain, if you localize at any maximal ideal, yeah, you get a discrete valuation ring. So this is a DVR. So this is certainly Gorenstein. Regular local rings are Gorenstein. So fiber is Gorenstein and closed fiber is Gorenstein and R is Gorenstein. That implies that this Rx localized at Q is Gorenstein for any maximal ideal of Rx. And therefore, this says that polynomial ring is Gorenstein. The same proof will work for power series. Exactly same proof will work. So I will leave that as an exercise that if R is Gorenstein, then R power series is Gorenstein. The converse clearly holds because X is a non-zero divisor. when you go mod in non-zero divisor, Gorenstein property is preserved, whether the ring is local or not. So if Rx is Gorenstein, then certainly R is Gorenstein. Or R power series ring is Gorenstein, then R is Gorenstein. Okay. Yeah, so that is the importance of Gorenstein property for the fiber. Okay. Yeah. Any questions so far? Yeah. Are there any questions so far? The Gorenstein property can be replaced by Cohen-Macaulay property, yeah, in this proof. So I have also given another proof that R, if R is Cohen-Macaulay, then polynomial ring over R is also Cohen-Macaulay. This I proved before, but this shows that to check whether Rx is Cohen-Macaulay, one has to simply look at the fiber. The fiber turned out to be very easy. It is localization of a PID. And that we understand it is a DVR. DVRs are Cohen-Macaulay as well as Gorenstein. Okay. Yeah. So this result will come at the end of a sequence of small results. So let me state the theorem. This is the main theorem we want to prove today. So we have a flat local homomorphism, RMK phi to SNL. This is a flat local map. This is the assumption throughout. Then, you see, to test Gorenstein property, we have to always check Cohen-Macaulay property. So Gorenstein rings are Cohen-Macaulay rings whose Sockle dimension is 1. Okay. To test Cohen-Macaulay property, I must know relation between depth and dimension. So depth has to be equal to dimension for Cohen-Macaulay property. Yeah. So we will establish these formulas for dimension of the base and the dimension of S and the dimension of the fiber. So first formula is the dimension of S is equal to dimension of R plus dimension of the closed fiber, S mod MS. Yeah, this is full dimension. Yeah. Second, if M extends to the maximal ideal, okay, and M is finite R module, finite R module of finite length then length of M as an R module is same as length of M tensor S as an S module. Okay. Third, suppose if Z bar equal to Z1, Z2, Zn is a regular, these are elements in S. These are elements in S, which is S mod MS regular sequence. So this is a regular sequence on the closed fiber. Then Z bar is also a regular sequence. This is S sequence. This is an S sequence, and this flat local map I can compose with S mod ZS, okay, S mod ZS, and then this is a flat local map. Okay, so if I want to get a regular sequence on S, this is the bigger ring. Okay, it is enough to check that it is regular on the fiber. Then it will imply that it is also a regular sequence on S. Okay, and I can compose the natural map from S to S mod ZS with phi to get another flat local map. then what is the connection between the depth? So we have same formula. Depth of S is depth of R plus depth of the fiber. Right? And once we have these formulas about dimension and the depth and the how regular sequence on the fiber becomes a regular sequence on S, you will see that the Cohen-Macaulay and Gorenstein property will come out as easy consequences. So S is Cohen-Macaulay if and only if R and the closed fiber are Cohen-Macaulay. Okay. Then S is Gorenstein if and only if R and S mod MS are Gorenstein. Okay. Yeah. So these are the 6 things we want to prove today. Any questions? These are all interconnected, and the main theorem are 5 and 6, which shows how to get Gorenstein property of S from R if you have a flat local map from R to S. Okay. So we have to look at the base and the fiber, and their Gorenstein property or Cohen-Macaulay property imply the same property for S, and vice versa. All right, so let us begin. Let us begin with the first formula, that dimension of S is dimension of R plus dimension of S mod MS. So let D be the dimension of R, and we apply induction on D. So let D be equal to 0. So R is Artinian. R is Artinian in this case, and therefore the maximal ideal is nilpotent. Maximal ideal is nilpotent for all large n. Mn is 0. Okay. This implies that Mns is also 0. S is an R module, and Mn is contained in its annihilator. Okay. So therefore, if Mns is 0, I'm looking at the ring S and going mod an ideal which is nilpotent. Okay. When you take a local ring and go mod nilpotent elements, ideal which is nilpotent, the dimension doesn't change because nilpotent elements are contained in every minimal prime. Okay. So this says that dimension of S mod MS is 0. Yeah. Dimension of S mod MS is 0. So
it is equal to dimension of S, no?
So how does it prove? Do you see that? This is 0. And this is equal to dimension. Dimension, because I go mod nilpotent ideal, dimension doesn't change.
Yes.
Yeah. Dimension of S mod MS is same as dimension of S. And so this formula is true. So 1 is true. Is this clear? Formula is true for Artinian local rings. And now I'm applying induction. And so I now assume that dimension is positive. Suppose dimension is positive. Suppose dimension of the base is positive. Okay. Now let n be the nil radical of R. Okay. And I have a flat local map. And flat maps, they are preserved under extension of scalars. So when I go to R mod n, tensor with R mod n, okay, this is also flat local. This is also flat local. Yeah. And if n is nilpotent, ns is nilpotent. So dimension of R mod n is also D, and dimension of S mod ns is equal to dimension of S. Okay. So from this flat map, I have passed to the phi bar, which is also a flat local map. But what is the relation between the fibers? Yeah, the fiber, closed fiber of phi bar is S mod ns, yeah, over m times S mod ns. This is same as S mod m, because ns is contained in the maximal ideal. So fiber doesn't change. Fiber doesn't change, and the dimension don't change if I pass to if I extend the scalars to R mod n. Okay, so we may assume that the nil radical of R is actually 0. By passing to R mod n, I can assume nil radical is 0. Okay. Now dimension is positive and nil radical is 0. So here is my maximal ideal, and nil radical is intersection of all the minimal primes. Okay. This is intersection of all the minimal primes. Right? So this means M is not contained in any of the minimal primes. Okay. So I can pick an X by prime avoidance. I can pick an X which is in M, not in any of the minimal primes. Because nil radical is 0 and dimension is positive. So M is not contained in the union of P. So I can pick an X, which is here. R is reduced. So this X is a non-zero divisor. This X is a non-zero divisor on R. Is this clear? We couldn't have picked up a non-zero divisor in the beginning, even if dimension was positive, because maximal ideal could have been associated. But after we go mod the nil radical, okay, it has become a reduced ring. And in a reduced ring of positive dimension, maximal ideal is not an associated prime. So I can pick an element in maximal ideal, which is a non-zero divisor on R. Okay. Yeah. So therefore, the multiplication map, this is injective map, because X is a non-zero divisor. And R2S is flat map. This is flat. So injective maps are preserved when I tensor with S via phi. Injective maps will be preserved, and therefore S to S, then multiplication map by phi. Okay, this is injective. So therefore, phi X is regular on S. Phi X is regular on S. So we had flat map from R to S, and X is a non-zero divisor. But then by extension of scalars, this is also a flat map. And the fiber doesn't change. The closed fiber is the same. Closed fiber of this map, phi bar is same of phi. Both are equal to S mod ms. Okay, so we started with a reduced ring and a flat map. Okay, and X is we could find a non-zero divisor, and the entire data descends to this flat map. The fiber remains the same, the dimensions go down. Okay, the dimensions are going down. This dimension of R mod XR is dimension of R minus 1, and dimension of S mod XX, because X is a non-zero divisor on X, on S, okay, dimension of, so when I write XS, the S is a R module V of phi. So this XS is really phi X S, okay? So dimension of S mod XS is also reducing by 1. And the fiber remains the same. So by induction hypothesis, I get that dimension of R is dimension of S is dimension of R plus dimension of the fiber. Is this calculation clear? Are you convinced that the dimension formula holds? Any doubt? Any doubt about this formula? Jai Singh, are you there?
Yes, sir.
Yeah, any doubts in the derivation of this formula for dimension? Okay. All right. So let's proceed. That is the first formula. Now we want to show that the length is preserved. Length of an R module, when I tensor with S, that is also preserved. Okay. So I have a flat local map of local rings, and M is length of a module. M is an R module of finite length. I want to show that the length is preserved. When I tensor, yes, the length is preserved. So suppose the length is N. Okay. That means I have a filtration. I have a filtration of submodules. I have filtration of submodules so that the quotient modules are isomorphic to R mod M. Mi plus 1 over Mi is isomorphic to R mod M. Okay. Now, R to S is a flat local map, and I have inclusion. Inclusions are preserved when I tensor with S. So I get the following filtration of S modules. This is 0, Mn minus 1 tensor S, M tensor S. Okay. So in order to compute the length of M tensor S, I must examine the quotient modules. Yeah, the quotient modules are Mi minus 1 tensor S over Mi tensor S. Okay. But this is isomorphic to Mi minus 1 over Mi tensor with S. This is R mod M tensor with S. This is isomorphic to S mod MS. But in this, I'm assuming that MS is the maximal ideal. So the quotients are simple modules, and this says that the length of M tensor S is preserved. Yeah. If maximal ideal of R does not extend to the maximal ideal, then also we can derive a relation between length of M and length of M tensor S. Yeah, we have to multiply by the residue field extension degree. That is S mod N over R mod M. Yeah, S mod N over R mod M. That is that degree has to be looked at, and the length of M tensor S will be length of M times the degree of the extension of the residue fields of R and S. Okay, so that is number 2. Number three, we want to, by using a regular sequence on the fiber, I want to produce a regular sequence on S. Okay, I have the fiber S mod MS, and suppose Z is regular here. Z belongs to S, and it is regular on the fiber. Then I want to show that Z is S regular. Okay, so this number 3 has 2 parts. That if an element of S is regular on the fiber, closed fiber, then it is regular on S. That is first. And second, I can compose the map from R to S to S mod Z, and this composition will also be a flat local homomorphism. Okay. So the statement is about regular sequences, but it is enough to prove it for one regular element, and then keep doing this. Okay. So main thing is to see that if an element of S is regular on S mod MS, then it is regular on S. Okay. Yeah. Right. So let us look at the following exact sequence for this: 0 to Mn over Mn plus 1 to R mod Mn plus 1 to R mod Mn. This is an exact sequence of R modules. Okay. And R to S is a flat local map. So I can tensor with S and preserve the exactness. So this means 0 to Mn over Mn plus 1 tensor with S to S mod Mn plus 1 S to S mod MNS. This is exact sequence of R modules, right? But let us look at Mn over Mn plus 1. So this is, suppose Dn is equal to dimension of Mn over Mn plus 1 over the residue field. This is vector space dimension. Dn is the vector space dimension of Mn over Mn plus 1. And so that means that Mn over Mn plus 1 is equal to K. It is isomorphic to K, direct sum of K Dn times. Yeah, this is R mod M, direct sum Dn times. Now tensor product and direct sum, they commute with each other. So when I take the tensor product of Mn over Mn plus 1, okay, that is isomorphic to S mod Ms direct sum Dn. Okay, so we have the following exact sequence: S mod Ms Dn, S mod Mn plus 1 S, and S mod MNS. Okay. Z is S mod MS regular. It is given to us. So then apply induction on N. Apply induction on N to see that Z is S mod MS MNS regular for all N. Yeah. So if N is 1, then it is equal to S mod ms d1 S mod m square S mod ms. So Z is regular here. Z is regular here because it is direct sum d1 times of S mod ms, and therefore it is regular here. You can apply the snake lemma and see that the multiplication map from Z S mod ms to S mod ms, this multiplication map is an injective map, and here also this is injective map. So this map is also injective because the kernel of this map is caught between kernel of this map and kernel of this map by snake lemma, and therefore this Z is regular on S mod m square S. And now go to n equal to 2 case, and you can reduce n equal to 3 case, and so on. So by induction, Z, which was S mod ms regular, is S mod mn S regular for every n. Is this clear? Yeah, but I want to show that Z is S regular. I have proved that Z is S mod mn S regular for every n. So let us deduce that this implies that Z is S mod ms regular. Okay. We want to now claim that Z is S regular. So suppose there is an element in S. Let U be in S, and U Z is 0. Yeah, U Z is 0. Then read this equation. Read this equation in S mod MNS. So this implies that U bar Z bar is 0 here. But Z bar is a non-zero divisor on S mod MNS. And so this implies that U belongs to MNS for all n. Yeah. Do you see that? What does it give for M, for U? U belongs to MNS. What can you say about U?
It is in the intersection. So
yeah,
U should be 0.
Right. So MNS intersection is 0 because MS, that's where we are using flat local map. That maximal ideal of R is going into the maximal ideal of S. So this MS is contained in the Jacobson radical, and so by rule intersection theorem, this intersection is 0. Okay, so U is 0, and therefore S is, Z is S regular. Okay, so what we have done, we had this flat local map, and then I had an element which is regular here. I have proved that the same element is regular on S. Okay, same element is regular on S. Right? Yeah, and then you can apply induction. But now the next part is to see that when I compose this map with the natural map from S to S mod ZS, then this composition is flat local. This flat local map. Yeah. So we want to show that S mod ZS is R flat. Okay. It is R flat via this homomorphism phi composed with pi. Okay. Now to prove that some module is flat, we have to calculate torr 1. Yeah. We want to prove that torr 1 is 0. Okay. But this is enough to prove that Tor 1 of R mod P S mod ZS is 0 for all primes P of R. You recall this result when flatness was discussed in Professor Sengupta's lectures. To prove that Tor 1 of R M comma ring is 0, it is enough to look at R mod P, because any module can be filtered over a Noethen ring. Yeah, we can filter a module so that the quotients are R mod P for various prime ideals, and then to see whether Tor 1 of M comma Z mod SZ is 0, it is enough to do it on R mod P. Yeah. So we want to calculate Tor 1. My screen has disappeared again. Just a minute. Something is going wrong with my. All right, can you see the screen?
Yes.
Okay, so we want to calculate Tor 1. So any idea about how to go about computing Tor 1 of R mod P S mod ZS? What did we just prove about Z?
Taking the causal complex.
No, Z is S regular.
S to S, multiplication by Z.
Right. So we proved that Z, which was assumed to be regular on the fiber, is regular on S. Okay. So we can look at this short exact sequence. And calculate the Tor. So tensor with R mod P. Okay. Tensor with R mod P. And to get long exact sequence of Tors. So we will get Tor 1 R mod P S, Tor 1 R mod P S, then Tor 1 of R mod P S mod ZS to Tor 1 R mod P S, tensor product. Now we have to descend to tensor product. So S mod PS, S mod PS to S mod Z PS to 0. So this is part of the long exact sequence of Tors. Yeah. So what can you say about this Tor? Tor 1 of R mod P comma S.
These are 0 because S is R flat.
Right. Yeah. When this is 0 because of flatness. Okay. So we need to prove that this is 0. This Tor 1 of R mod P is 0. S mod ZS, but that is equivalent to proving that this map is an injective map. So Tor 1 R mod P S mod ZS is 0 if and only if this map PS is injective. Yeah. Do you see that this is injective? How to show the so to show that multiplication by Z is an injective map, we have to see that it is a non-zero divisor on S mod PS. Yeah, this is same as proving that Z is a non-zero divisor on S mod PS. But R2S is flat local. And so by extension of scalars, by extension of scalars, R mod P to S mod PS, this is flat local. Yeah, this is flat local. And what is the relation between the fibers? Closed fiber of phi bar, closed fiber of phi bar. The PS, P is a prime ideal of R. So P is contained in M. So PS is contained in MS. And so the closed fiber of phi bar is also S mod MS. Yeah. So I have flat local map, R mod P to S mod PS. The fiber is S mod MS, but Z is regular on S mod MS. Yeah. So it will be regular on S mod PS. We just proved that. If some element of a ring is under flat local map, if you take an element of S and it is regular on the fiber, it is regular on S. Yeah. So the fiber of phi bar is same as S mod MS. Z is regular on S mod MS, and therefore Z is regular on S mod PS also. So that proves that this multiplication map by Z on S mod PS is injective, and therefore TOR1 is 0. So S mod PS, Z is injective map, and therefore TOR1 of R mod P S mod ZS is 0. And this means that S mod ZS is R flat. So I had a map, flat local homomorphism, and Z was regular on the fiber. It turned out to be regular on S also. And that has helped us to extend this flat local map by one more map from S to S mod ZS. And this composition is flat. This is also flat local. So now I can just apply induction. If you have a regular sequence on the fiber, it will remain regular sequence on S, and you can keep on composing and extend this to S mod Z bar S, where Z bar is a regular sequence on the closed fiber. Is that clear? Is this clear? Any doubts on this? All right. So now we are ready to prove the formula about the depth. Okay. So I have a flat local map, and I want to relate depth of the base with depth of S and depth of the fiber. All right. Okay, depth has to do with the maximal regular sequence. Yeah. So choose a maximal regular sequence in R. So let X bar be equal to X1, X2, Xn be in the maximal ideal of R, and it is R regular sequence. Now we have flat local map, so it implies that this is regular on S also. Okay, this is also regular on S. So X bar is S regular sequence. Okay, it's a S regular sequence. And by extension of scalars, R mod XR to S mod XS is flat local map. It's a flat local homomorphism. Yeah, with the same fiber. the fiber is the same. The closed fiber is the same. S mod XS over M times S mod XS is S mod fit to S mod MS. The fiber doesn't change. We have a maximal regular sequence in R. It remains it's a regular sequence on S. Okay. And now the depth reduces. Depth of R mod XR is 0 now. Okay. Depth of R mod XR is 0. I have preserved the flat local map by extension of scalars without changing the closed fiber. Okay. So we may assume, therefore, and the depth of S has also gone down. So this you want to prove this formula. Depth of R is depth of S plus depth of the fiber. So I can, from R to S, I can pass to R mod XR to S mod XS, because both the depth of S and depth of R have reduced by N without changing the depth of the fiber. So we may assume, therefore, depth of R is 0. We may assume depth of R is 0. Yeah, depth of R is 0. So, yeah. So then once the depth of R is 0, okay, we have to show that depth of S is 0 and depth of S mod MS is 0 to prove this formula. Yeah. So choose a regular sequence in S mod MS. Sorry, I have a mistake here. Depth of S is depth of R. R and I am interchanging. Yeah. So this depth of R I am reducing to 0. So I need to now prove that depth of S is depth of S mod MS. Okay. Need to prove depth of S is same as depth of S mod MS. Yeah, do you see why this is true? What did we prove just now? We take a regular sequence on S mod MS. Okay, regular sequence on S mod MS. It will be a regular sequence on S. Yeah. So if Z bar is a maximal regular sequence, these are elements in S, maximal regular sequence on S mod MS, then Z bar is S regular sequence. Okay, and R to S mod Z bar S is flat local map. Okay, but what is the depth of S mod ZS? Z bar was maximal regular sequence on S mod MS, then it is a regular sequence on S. So this is equal to depth of S minus, suppose this length is N, this depth of S minus N. Okay, but this Z bar was maximal regular sequence S mod MS. So what is the after you go mod, if you take the closed fiber here, the closed fiber here doesn't change. Okay, closed fiber here doesn't change. So yeah, so R2 S mod ZS is flat. S mod ZS Okay, this flat map, but now the depth of the fiber has become 0. So R2 S mod ZS has a closed fiber of depth 0. Yeah. But we already have reduced to the situation where depth of R is 0. Depth of R is 0 and depth of the closed fiber is also 0. Okay. Yeah. So to prove the formula, we will just show that depth of S is also 0. So need to show depth of S is 0. But a local ring has depth 0 if the maximal ideal is an associated prime. This is true if and only if S mod n embeds into S. Yeah. But depth of R is 0. This implies maximal ideal is associated. And this implies R mod M injects into R. Okay. But S is R flat. So this injection is preserved. S tensor R tensor S is S. So this is an injection. Yeah. But S mod MS has depth 0 because I went mod maximal regular sequence on the fiber. So S mod MS is a finite S module of depth 0. Okay. So therefore, the residue field of S injects into S mod N injects into S mod MS because S mod MS is depth 0. So S mod N is injecting into S. So that implies depth of S is 0. Okay. So in this formula, depth of S is depth of R plus depth of S mod MS. Okay. I reduced to the situation where depth of R is 0. And then we had to prove that depth of S is depth of S mod MS. But then I went mod a maximal regular sequence on S mod MS. And that turned out to be a regular sequence on S. And the closed fiber was preserved. And here we have proved depth of S is also 0. So this formula is true. Are you convinced this is correct? The formula for depth is correct. Any doubt on this?
Sir? Hello.
Why is S mod N contained in S mod MS?
Yeah. S is R flat. S is R flat. So, and depth of R is 0. Depth of R is 0. So R mod M injects into R. Yeah.
Okay.
And then tensor with S.
Okay. So this part is okay.
Yeah. So S mod MS injects into S.
That is okay. But this one.
S mod M.
Yes.
So S mod MS is the closed fiber. After I go mod the maximal regular sequence on S. Okay.
Okay. I got it.
I took a maximal regular sequence on S mod MS. That was a regular sequence on S also. And then I composed it with S mod ZS.
Yes.
Okay. So S mod MS has depth 0 after I go mod maximal regular sequence, and therefore S mod N injects into this.
Yeah. Thanks.
Okay. Yeah. So depth formula is proved. Dimension formula is also proved. Just put them together. Okay. So what we have proved is that we have a flat local map. of local rings, and then the depth of S is depth of R plus depth of the fiber. We have also proved dimension of S is dimension of R plus dimension of the fiber. Okay. Now let us prove the Cohen-Macaulay property, descent and ascent of Cohen-Macaulay property. That S is Cohen-Macaulay if and only if R and S mod MS are Cohen-Macaulay. Okay. Yeah. So suppose S is Cohen-Macaulay. Then the depth of S is dimension of S. So we have equality here. So that says depth of R, okay, plus depth of S mod MS is equal to dimension of R plus dimension of S mod MS. Okay, but depth of R is less equal to dimension of R. Depth of S mod MS is less equal to dimension of R. If they have become equal, then these are individually equal. So R and S mod MS are Cohen-Macaulay. And you can reverse. All these steps can be reversed. Yeah, is this clear? Any doubts on the ascent of Cohen-Macaulay property? If we have flat local map from R to S, if I know R is Cohen-Macaulay, I can deduce S is Cohen-Macaulay by testing the Cohen-Macaulay property of the closed fiber. Okay. Now the last property, that is the main result today, that S is Gorenstein. If and only if R and S mod MS are Gorenstein. Okay. Now we will use this characterization of Gorenstein property that ring is Gorenstein, TMT is Gorenstein, if and only if T is Cohen-Macaulay, and the circle of T mod any system of parameters to go mod, the circle dimension is 1. Remember, that is the classical definition of Gorenstein rings, that all system parameters are irreducible ideals. But irreducibility of a system parameters can be tested by going mod this ideal and then checking that the circle dimension of this local ring T mod X T is 1. Okay. So in this if and only if property, S is Gorenstein, if and only if R and S mod MS are Gorenstein, Cohen-Macaulay property is already taken care. Okay. So this 6 is reduced. This is reduced to proving that the circle dimension, suppose I take a maximal regular sequence on S, okay, and go mod, then calculate the circle, okay, then this dimension is 1 if and only if circle dimension of R and circle dimension of S mod MS are 1. Okay, and we can reduce to depth of R and depth of S and equal to 0. Okay, so Gorenstein property is preserved under going mod a regular element. Okay, okay, if T mod T is Gorenstein, if and only if T mod XT is Gorenstein, if X is a non-zero divisor, X is a non-zero divisor on T. Okay, So look at this depth formula. I can reduce this situation where depth of R is 0. Okay, and then I will apply induction on the depth of S mod MS and reduce to depth of S mod MS also equal to 0, like we did in the formula when we derived the formula for depth. Okay, we first reduce to depth of R equal to 0. Yeah, so Gorenstein property goes back and forth when you go mod a regular sequence, right? And then reduce to depth of S mod MS equal to 0, and that property is also preserved to go back and forth to going mod a non-zero divisor. Yeah. So therefore, we can reduce to the situation where all these rings have depth 0, as we did in 5. Okay. So using the proof of 5 implies that we can reduce to depth of R equal to depth of S equal to depth of S mod MS equal to 0. And same case with dimension. So these are Artinian local rings. So now we have R is Artinian local ring, S is Artinian local ring, and S mod MS is also Artinian local ring. Okay, we have these 3 Artinian local rings, and I have a flat local map from R to S. Okay, this is flat local map. Okay, and I want to then relate the Socle dimension of R, Socle dimension of S, and Socle dimension of the closed fiber. So we want to show that the Socle dimension of S equal to 1 if and only if the Socle dimension of R equal to Socle dimension of S mod MS equal to 1. Yeah, that amounts to proving the Gorenstein property. Okay. Yeah. So what we will prove, we are going to show. So Socle dimension of a local ring, Socle dimension of a local ring T, that is denoted by type. It is called the type of T. Okay. It's called the type of T. So we are going to prove, we shall prove that type of R times type of the closed fiber equal to type of S. So let's call this as R. Let's call this by F, and let's call this by S. So we are going to prove that RF is equal to S. And that will say that if S is 1, then R and F are 1, and vice versa. So it will prove the Gorenstein property of these Artinian local rings under flat local pattern. Is this reduction clear? Any doubts that we can reduce the general case to the case of Artinian local rings with S mod MS is also Artinian local ring? And then we will prove this relation between type, that the type multiplies. Type of the base times type of the fiber is type of S. Okay. But what is type of R? Type of R is the dimension of the Socle. Okay. Right. So this is R. This means HOM R mod M R, which is the Socle. Yeah. This is isomorphic to R mod M R. Yeah, I hope this is clear. HOM R mod M comma R is the Socle. It is isomorphic to the Socle of R. And I am assuming type of R is R. So this is the R-dimensional vector space of the residue field. Okay. Now, R2S is a flat local map. R2S is flat local map. Okay. This flat local map. So 0:M S, 0:M is an ideal in R. Okay. So when I tensor colon, okay, you can read this proof in Matsumura. This is equal to 0:MSS. Yeah. Flat module distributes over colon of ideals. But this is K to the R. This is R mod M to the R. This direct sum, tensor product distributes over direct sum. So this is also isomorphic to S mod MS R. So 0:MS is equal to S mod MS R. Okay. We are coming close. We want to relate this to the socle of S. Okay. Socle of S. Right. Now let's look at the socle of S. Socle of S is 0:N. This is the socle of S. S is Artin local ring. So this is the socle of S. And the socle of S is S dimensional. So this is isomorphic to S mod its maximal ideal to the power S. Okay. But this is by the same principle. This is Hom S, S mod N, S. Okay. Yeah, that is this Hom. Okay. But this is isomorphic to Hom S, S mod N, Hom S, S mod MS, S. Do you see why this is true? Can anybody explain me why this is true? What is the tensor product of S mod N with S mod MS? Anyone? S mod N tensor S mod MS.
S mod N.
S mod N.
Yes.
So do you see this now?
Yes.
Why this is true?
Because home of this will be home of P comma home of N comma M is home of P tensor M comma N.
Right. Hom tensor duality.
Yes, yes.
Adjoint property of Hom and tensor. So this Hom, this is equal to Hom S, S mod N tensor S mod MS S. But this is S mod N. Right? So let us continue. Okay. So this is equal to Hom S, S mod N. And what is this Hom? Hom S mod MS S. Hom S mod MSS is 0:MSS, right? This is isomorphic to Hom S, S mod MSS. So this is 0:MS, but 0:MS is isomorphic to S mod MSR. Okay. So this is S mod MSR. This is direct sum. of Hom S, S mod N, S mod MS. Okay, R times. What is this? Do you recognize this? Hom S, S mod N, S mod MS. What is Hom of S mod N, S mod MS? S mod MS is S module, right? It's an S module and
fiber.
socle of the fiber. Very good. Yeah. So that says, so we started with the socle of S, that was what L to the power S. This was the socle of S, because socle of S is S dimensional. This is isomorphic to residue field of S times. Okay, but this last formula says that this is direct sum of the socle of S mod MS R times. But socle of S mod MS, that is, I'm denoting by F. So this is equal to dimension equal to F times R. So S is equal to FR. Yeah. That shows R is Gorenstein and fiber is Gorenstein if and only if S is Gorenstein. Any doubts? So we have proved all the 6 results, all the 6 formulas. And our purpose was to see that the Gorenstein property is passed on to completion from a local ring. It is passed on to polynomial ring. It is also passed on to power series ring. Okay, so our time is finished.